Hello everyone. In this lecture, we will learn what are the properties of red-black tree and its logical behavior in data structures. As an overview, we will learn the content of the given topics mentioned below as definition of red-black tree, properties of red-black tree, balancing in red-black tree, and scenarios in red-black tree. Red-black tree is another self-balancing tree just like the AVL tree. Comparably, in red-black tree, each node has extra bit of information often interpreted as red or black color. This bit of information in a node is used to ensure time complexity of big O log n at any given time for operations such as insertion, search, and deletion. Bit of information can be interpreted by the types in Java using Boolean or integer or using enumeration. We will be using integer to determine the color of a node in red-black tree in upcoming lectures. Red-black tree is a binary search tree and has the following properties. Every node is either red or black. The root of tree is always black. Every leaf, which means null nodes, are black. If a parent node is red, then its children are black. Every path from a node, including root node, to any of its descendant null node has the same number of black nodes. So let's see 5 defined properties and how they are correlated with the given red-black tree in this example. Every node is either red or black, so you can see that we have red and black nodes in the red-black tree. Root node is always black. Every leaf node is black. This is important to know because it plays key role at the reformation of red-black tree, which we will see in the upcoming slides. If a parent node is red, then its children are black. So here you can see that red nodes also have leaves that are black, which in this case considered as their children nodes. Every path from a node, including the root node, to any of its descendant null node or leaf node has the same number of black nodes. So this said, if we take 62 as an example, going down from right subtree or left subtree of node 62 gives same number of black nodes as a result. Next, let's take node with a key value of 39. From left subtree there is 35, which is a black node. And right subtree there is 48, which is also a black node. This makes it one black node for each side, and when we go down in each side there is one additional null black node in each side for both descendants. 35, 24, null. 35, 38, null, or null this side. And 48, null. So from 39 to any of descendant node there are two number of black nodes. Before we jump into red-black tree insertion, we should remember the rotations of the AVL tree. AVL tree rotations are dependent on the structure of the binary search tree. However, in red-black tree there are two properties that influence how the tree is balanced. In addition, red-black tree doesn't require an additional checkup for a term called balance factor to know if the tree is balanced or not. But instead, in red-black tree, balancing is done automatically by knowing the rotation rules in which we will learn at the upcoming slides. So this said, let's look at two types of balancing properties of red-black tree. Those are one, recoloring, and the second, rotations and or recoloring. There are 4 scenarios in red-black tree, and red-black tree doesn't require an additional checkup such as balance factor in AVL tree. Instead, red-black tree balances itself automatically depending on the cases, which I will be mentioning very soon. So let's assume Z is the last inserted node in the red-black tree. This is for insertion case, but same case is acceptable for deletion as well. In deletion, however, the termination of Z node differs depending on the deleted node. So this said, let's have a look at 4 scenarios that is used to balance red-black tree. First, if Z is root or root is red, then we color it back to black. We remember this from previous slide, where root should always be black in red-black tree. Second, if Z's uncle is red, then we just do recoloring. If Z's uncle is black and we have left-right or right-left case, the same cases in AVL tree, then we rotate the Z's parent. If Z's uncle is black and we have right-right case or left-left case, again the same cases which we know from AVL tree, then we rotate Z's grandparent and do recoloring. Let's see the given definitions with a theoretical example at the next slide. So let's assume we are inserting node 72 in our red-black tree. As a reminder, I want to mention that we always have red starting when we make insertions in red-black tree. This is because starting with a black node could violate the property mentioned in slide number 4, where every path from a node, including root node, to any of descendant null node should have the same number of black nodes. If you remember other property where if a node is red, then its children should be black, but if a node is black, then it would be inserted regardless of the color of the parent node and any of its predecessor nodes. This behavior would most of the time violate the definition of red-black tree mentioned in slide number 4 at the 5th property. Hopefully I cleared this out for everyone watching this lecture, but as a result, you should know that inserted node better be starting and having color red. So let's go on and add node 72 to our red-black tree. Node 72 would be located at the left pointer of node 74. So our last inserted node is Z, and a question comes in here for all of you. So what node is the uncle of node 72 then? I will wait for some couple of seconds and I will answer this question. If you said it's node 71, you are incorrect. This is where the importance of defining null node color comes in. If you remember, a null node or leaf nodes are always black. So this is important because then the algorithm will work consistently correct. Because if we didn't know the color of a null node, then we wouldn't be able to determine the uncle node for node Z. And yes, now you guessed correct. Uncle of node Z is actually null node, that is node 87's right pointer. And we have scenario number 4 for balancing the red-black tree. Z's uncle is black and we have left-left case which requires to rotate Z's grandparent, which is node 87. And we do recoloring. So let's see it in action. Left-left case, rotation, and recoloring. Next, let's insert node with key value of 69 in our red-black tree. We have right case and the uncle is black null node, which is the left pointer of node 62. So we do the same, this time rotating left, the grandparent node, and recoloring. Next, insertion of node 83 goes to the left of node 87. So what is the uncle node here? If you said it is node 72, you are correct. So which scenario this fits into? It fits into scenario number 2, where uncle is red and only thing we do is recoloring. Here theoretically, you have seen how iteratively our nodes would be recolored. And during this process, we would also satisfy scenario number 1, where if root is red, we should recolor it to black. Next, node 85, where we will try to satisfy last remaining scenario, which is scenario number 3. We have left-right case, and we have a black null uncle, which is located at the right pointer of node 87. So we rotate the Z parent. We don't finish it here because now we have scenario number 4, where we need to rotate Z's grandparent and do recoloring. In this lecture, you have learned what are the properties of red-black tree and its logical behaviors in data structures. In the next one, we will have a look at insert operation with more practical tasks to see how those behaviors actually performed using the code example. I hope you enjoyed this lecture. I hope to see you in the next one.